Okay, sorry, I just accidentally pressed the stop button for the video. So let me just continue. Actually, it's not the end for the problem. Now, in general, we don't have cancellation for congruence. Okay. For example, so we have 4 congruence to 2 module 2, right? But we don't have now you divide both sides by 2, then what happened? We don't have 2 congruence to 1 module 2, right? Now one of the reasons why we don't have it because it's a similar concept in division, okay? Because division we cannot divide something by 0, right? And here one of the key reasons why we don't have the cancellation because the number that we want to cancel, for example, in that example, is in fact congruent to 0, right? Because you want to divide it by 2, but 2 is congruent to 0 module 2. So one of the reasons why we don't have it because we just we just cancel. I mean, we just try to divide by something by 0. But anyway, so this is not true. I mean, you cannot cancel numbers for congruence relation. Of course, in some special occasion, you can do that. Okay. Anyway, so we back to the problem. Now we have this. Okay, for this problem, that is important because this is not congruence relation anymore. Okay, the part I just highlight is a equation. So that's why you can do whatever you like as long as you're not dividing by 0. Okay, for example, you can cancel m, right? You have m appear everywhere in that equation, right? And you can also multiply the whole equation by d. So hence we have this. Okay, you manipulate this equation, you multiply it by d and then divide by m, then you get this. T1 equal to T2 plus dn. Okay, that is important. Why so important? Because and we have, okay, and we have this. Okay, if you put the other numbers to the other side, I mean, for example, you move T2 to the left, then you get T1 minus T2 with the absolute value. Okay, with the absolute value, okay, equal to d times the absolute value of n. Okay, now d, remember d is GCD, so d must be positive. But for T1 and T2, of course, T1 and T2 they are non-negative because they are from that set. But when you take the difference, we don't know. The difference can be zero, can be even negative. But if you take absolute value, okay, that's another story. If you take absolute value, of course, the value will be non-negative. Now, because in particular, remember what are your choices? You say that T1 and T2 they're different. Okay, you pick different members. So T1 minus T2 cannot be 0, right? Because otherwise that means they're the same. But here, because they're different, so T1 minus T2 must be non-zero. In particular, the absolute value. So T1 minus T2, the absolute value must be strictly bigger than 0. Okay. Now, what is the problem? Now the problem is, you know that now here, T1, T2, they are taken from that set. Okay. Now, if you take the difference, okay, you can draw a diagram. Okay, for example, you draw a number line, and you locate, for example, T1 and T2 in between 0 and d. Okay, because I mean they cannot be outside that range, right? So T1 minus T2, the difference must be strictly less than d. Okay, that is the consequences. In particular, in particular you have, okay, particular t1 minus t2, the difference must be strictly less than d. Okay, but how could that be possible? Because now you see this number, okay, this number is less than d, right? This number is less than d, but this number is equal to multiple of d. The only possibility is this multiple must be 0, right? Because remember, what is this? This is an integer. Now after you take the absolute value, it's a non-zero integer. I mean non-negative integer. It can be 0, it can be positive. I mean it can be 0, but now if that is 0, then it will force t1 equal t1 minus t2 must be equal to 0. But we know that is impossible. Okay, so let me just make it more clear. Now, because we must have n, that number must be bigger than 0. So, okay, otherwise, okay, why? Because otherwise t1 equal to t2. So we have this. We have this number t1 minus t2. This number must be strictly bigger than d. So which is impossible. Because you see, now we have contradiction already. On one hand, we say that, okay, the difference must be less than d, but on the other hand, t1 minus t2 is okay, it should be bigger than or equal to d. Okay, or as I said, larger than or equal d. Okay, which is impossible. Okay, so you have something which is strictly less than d, but on the other hand is larger than or equal to d. I mean strictly less than d, right? Strictly less than d, which is this part. But on the other hand is also larger than or equal to d, which is impossible. Okay, so that's why we got a contradiction. So why we have a contradiction? Because I'm saying that even though you pick some members, okay, from that set, okay, but you say that they are congruent. In fact, they cannot be congruent. They must be incongruent. So that's why you got something impossible. So that means this number. Okay, so let me just copy that. So this number and this must be incongruent modulo m. Okay, so we proved the first part. We just show that, okay, if you have two members from the solution, okay, then they cannot be congruent. Okay, from the set that, okay, you take t from 0, 1, 2 up to d minus 1, okay, then you must have something incongruent. Okay, so we proved the first part. Now the second part is what? We still have to show if you have some other solution, then that solution must be congruent to some of those members. Okay, so let me do it. The second part is if we have a solution, okay, for example, x equal to x0 plus this, because we know the solution must be in this form, okay, but we just don't know whether that is congruent to some of those members when you're choosing t, okay, from that set. Okay, so that is the second thing you need to show. We have another solution for some integer t. Okay, now for example, with t, okay, bigger than or equal to d, okay, because if the integer is less than or equal to d, then it's just Okay, if otherwise, if t is less than d, then t must be from the set of integers like this. Okay, then of course that is a solution from the original from the solution set we just mentioned at the beginning. Okay, but now you have another solution. We want to show that solution must be congruent to those members. Okay, now how can we show that? Now, then of course you can use anything you like. Okay, for example, by division. By division, okay, we can find some integer, okay, k, such that actually this t, okay, or okay, that t prime, okay, for example, okay, t prime, okay, is just equal to t plus kd, okay, kd, okay. That means you sort of add some multiple of d, okay. Now that k can be negative, okay, depending on the value for your t, okay. If t is very big, okay, then you might have to add some negative multiple of d such that you bring it back to the range, okay, within d, okay. Otherwise, if this is otherwise if t is very small, okay, then you just add some positive multiple of d. Again, you just sort of bring it back to the range from 0 to d, okay. And the purpose, as I said, you just have to make sure this t prime is inside the set. This set. Okay. Now why? Why do you have to do that? Because now, of course, you just check it what happened. Now this number, okay, this number, now that's t prime, okay, m over d times t prime. Now you put it back, okay, using this relation, okay. Now that exactly give you this m over d times, okay, you simply do a substitution because now I want to compare x0 plus m over dt prime and the original solution, this, okay, m over d times t, okay. Now you see t prime is from this set, so this is one of the members from the incongruent, from those d many incongruent solution. So if you can show that in fact this solution is congruent to the original solution, this one, then you're done, right? Now let's see why they're congruent. Now after you do substitution, okay, you can multiply this m over d into the bracket, okay. Now even though, remember, this is m over d, it's not a fraction because d is a factor of m, so you can always cancel that, okay. Anyway, now this is equal to x0 plus m over d times t, and then plus this, you multiply kd with this fraction. Now that d got cancelled, you only get km, okay. It's a multiple of m, so that means after you take the congruence, so you take the congruence, so you take the congruence, and this number, okay, this number, I'm going to copy that again. This number is equal to x0 plus m over d times t modulo m, right? That means, hence, we have this number, okay, this is a congruence to this. This is the thing I just want to show, okay. because now this number is the original solution, okay? But this solution is something inside, I mean not inside, but those one of the member from those D incongruent solution we just got before, okay? But now I just proved that, okay, and in fact, by some choices of your T prime, okay, you can sort of make that general some other solution to be congruent to some of the member here. So in fact, that means, therefore, those solutions given by this are the only congruent solution to this problem. Okay, so we just prove it. Okay, it's fairly complicated, but it's not impossible, I would say. Okay, because you can still follow it. Okay, but of course it's a bit abstract. But in fact, if you apply that to some examples, that would be very convenient. Okay, so let's just do one example. Okay, for example, okay, now consider 3x equal to 6 modulo 9. Okay, now since GCD of 3 and 9 is equal to 3, and we know that 3 divides 6, okay, so there must be solution, in fact infinitely many solution to the problem. Okay, to the problem. Okay, now you can solve it by inspection or whatever observation by Euclidean algorithm. You can check that x0 equal to 2 is a solution. Okay, and the incongruent solutions are given by, so if you're asking for incongruent solution, there are not many, are given by this. Okay, given by x equal to x0 plus, now you know why we have 9 over 3, because this is exactly 9 is the number inside the modular class, modular congruence 9, and then you divide that by the GCD, so that's why you have 9 over 3, and it's given by this t. For t, now you are not having many choices, 0 to 1, 2, up to 2 minus 1, right? But 3 minus 1, right? But 3 minus 1 is exactly 2, so you only have 0, 1, 2. Okay, so that means x equal to x0 plus this number. Oh, sorry. Okay, let me just type it. Times 0. That is equal to 2. This is one solution. The other one is this. But this time you multiply by 1. So that gives you 2 plus 3. Okay, 2 plus 3, that is 5. And for the final one, you have x0 plus this 9 over 3. This time you multiply 2. Then you get 2 plus 6. That gives you 8. So that means x equal to 2, x equal to 5, and x equal to 8. Those three solutions are the incongruent solution to the problem. All other solutions will be sort of congruent to these three solutions. So therefore, hence x equal to 2, 5, 8 are the only incongruent solutions to the problem. any other any other solution will be congruent to that. Okay, if you don't believe that, you can try. Okay, check, for example. Check. It is easy to see that. For example, you take I don't know, you take 2 plus 30. Okay, that will give me equal to 32. Okay, 32. Okay, if you multiply 32 by 3, that gives you 96. Okay, 96, if you subtract it by 6, that will be equal to 60. Okay, so anyway, let me just show it in full detail. So 32 is a solution, right? And now 32 is congruent to one of those solutions. So which solution? 5. Okay, modulo 9. Since 32 minus 5 is 21. Okay, and 21 is congruent to 0 modulo 9. So that means even though you have another solution which is 32, right? But 32 is nothing but just 5 after you take the congruence modulo 9. Okay, so that's why I said you only have 3 different incongruent solutions to the problem. Okay, so we got it. Now before the end for the video, let me just give you a very special case. Okay, as a remark. Okay, so if you have a solution for the congruence relation, ax congruence to 1 modulo m, with, of course, you have to be careful about the GCD requirement. GCD of a and m equal to 1. This solution has a special name. It's called the modular inverse of the number a. Okay, modulo m. And sometimes we just denote it by, and it's denoted by bar of a. Okay, so because here I cannot type it. Okay, can I type it? Let's see. No, I couldn't type it. Okay, anyway, so this is like you have the letter a, but you put a bar on top of a, so it's the bar a. Okay, so just a notation. Okay, so for example, consider 7x congruent to 1 modulo 48. Okay, then in fact you can see that x equal to 7 is a solution to the problem. In particular, this you can check it because now the GCD is equal to 1. So there's only one incongruent solution to the problem. Any other solution will be congruent to 7. You can try any other problem will be congruent to 7. Okay, and so the modular the modular inverse of 7, you have to specify what congruence you're taking. Modulo 48 is 7 again. So 7 has inverse equal to 7, which is itself. So of course the inverse is not exactly what we mean for the usual division. So this is like you divide that a to the right, because see ax equal to 1, right? In the very usual sense, you just divide a to the right, then you get x equal to 1 over a. But now you're not doing it, okay? But in the sense that you're solving another equation and then you get a solution. And we just call that solution to be the inverse. So it's a similar concept but not exactly the same, okay? In particular, we don't have a fraction. We have a number, we have an integer, okay? So that's the end for linear congruence. So let me just stop here.